Hello, everyone, and welcome to this episode of the Inspiring Science Education Hangouts. Each month, we work to bring you a variety of different astronomy educational tools that you can take back to use in your classroom. And we're working to create an entire set of about 20 different lessons that will help you learn all the big ideas that there are in astronomy. Today, we're going to be talking about the Big Bang, that moment in time that, well, brought everything that we are and that our universe has into existence. It's the moment that time started, and it's the moment that all matter and energy popped into existence. Now, it didn't pop in appearing the way we see it today. It's taken time to evolve and change. And today we're going to be talking about the variety of different lines of evidence that we have that help us understand the Big Bang did happen, and our understanding of what our universe is shaped like and made of are actually based on reality rather than just stuff that sounded good. Joining me, I have Xavier Dupac, who is here coming to me from the European Space Agency facilities in Madrid. He works on the Planck mission and is someone that actually is helping us refine our understanding of the first moment that, well, there's evidence of our universe existing. We can't actually see anything before that moment, but that moment, which is the moment the cosmic microwave background was formed, is that first observable moment of the universe. Can you tell us a little bit about what you do with the Planck mission, Xavier?
So, hello everyone. Thanks for having me here. Okay, so what we do with the Planck satellite mission is that we make maps of the full sky in microwave. So the reason we do that and the reason we chose microwave emission is that this is where we have the most of the emission of the cosmic microwave background. So as Pamela said, the cosmic microwave background is in fact the first light that can be observed in the universe. It's not really the first light of the universe because, of course, light and some matter existed since a fraction of a second after the Big Bang. But actually, during the first 400,000 years after the Big Bang, the universe was mostly opaque. So it was impossible for light to travel in free flight. So at some point, the universe became less dense, so that it was possible for atoms to form and for the light to travel freely. And that moment is when we start observing the cosmic background.
And this is actually a really interesting point in time. Up until this point, the universe had been so hot that electrons and the cores of atoms, the nuclei of atoms, were all flying around completely free. So you had individual protons, you had a few protons that were coupled together to form helium. But for the most part, it was free electrons, free nuclei. And at the moment the cosmic microwave background formed, things finally cooled off enough that the electrons could suddenly buddy up with atomic nuclei and form normal atoms. And this essentially saved a lot of space, and photons could travel without being constantly absorbed and re-emitted, which was their fate prior to this moment. Does that sum it up?
There are two effects here. At roughly the same time, we have the universe moving from a plasma, basically. So plasma is just like a gas, but with charged particles. In that case, the charged particles were mostly protons and electrons. So most of the nuclei were in fact just protons, just hydrogen nuclei. And there were, as you said, a bit of helium and just a little bit of lithium and beryllium too. So number 3 and 4 in the table. But then at this point, so actual gas formed, neutral hydrogen formed, so the first atoms. And at the same time, the universe had become large enough already, the space had expanded enough. So, and at the same time the temperature had cooled enough so that everything comes together, and then the light, so what we observe today to be the cosmic microwave background, starts to exist. And in fact, at that time, the cosmic background was not at all in the microwave. It was in fact in the ultraviolet radiation, because this is the dominant radiation emitted by a hydrogen atom that forms from a proton and an electron. But of course, what happened since then is that we're talking about now from coming from 400,000 years after the Big Bang till today. And so present time, we are now 13.8 billion years after the Big Bang. So during all this time, the universe went on expanding, and at some point even accelerating. And this expansion also made the wavelength of these photons increase. So together they have increased since the time of the cosmic background by more than a factor of 1,000. So which explains that now we observe them in the very large wavelength, so the microwave, around the millimeter wavelength, whereas they were first created in the ultraviolet radiation.
Now, when we look at the cosmic microwave background, every new spacecraft, every new mission seems to get higher and higher resolution images. And what used to be the smooth gradient of very small variation is now basically pinpricks of variation. I'm going to go ahead and pull up the Planck map of the cosmic microwave background. Now, in general, hydrogen's going to deionize, is going to go from free electrons and protons to being a neutral hydrogen atom at pretty much the same temperature. What's up with all the variations that we see in the cosmic microwave background?
Okay, so if you look at the map like this, okay, you see the spatial angular variations here. In fact, it's hugely overprinted, because in fact these fluctuations are less than 1 in 100,000. They're in fact very tiny fluctuations over a very isotropic background. So here we really need very, very precise measurements to be able to make this kind of maps, because we're talking about mapping differences which are less than 1 in 100,000. So here you see the map of the full sky. If you look at so here you only see the cosmic background. So we have already filtered, let's say we have already removed all the other components that we observe, because we don't see directly the cosmic background. We see all kinds of things in the foreground. First of all, we see our own galaxy that also emits in microwave and far infrared. We see a lot of emission from the dust. We see emission from the free electrons in the galaxy. We also see some external galaxies, clusters of galaxies, and many other things. And what we see in the background is in fact, the fluctuations of the cosmic background. So these fluctuations are, first of all, they were, in the first place, quantum fluctuations in the very early universe. So you know that the quantum theory says that you can't be absolutely sure of your position or your speed. So this means that, you have to have some kind of a freedom, let's say. And so this creates seeds for the fluctuations that we see today. These were really tiny quantum fluctuations that were hugely amplified by various phenomena before what we see here in this map. So before the actual cosmic microwave background was emitted, these fluctuations were amplified by a number of physical phenomena. And then after that, after we see this print of the early universe, that is the cosmic background, in fact, these fluctuations are going to go on expanding. That is to say that the overdensities or over temperatures here, which are the same as the overdensities, are going to become more and more dense, and the underdensities are going to become more and more void. So they are going to create the large voids that we see in the large-scale structure of the universe today. And on the other hand, the denser regions, so the ones we see in red here, are going to form the large-scale structure. so are going to form the cluster of galaxies, superclusters, and so on.
So I went and I found one of the images that Planck took that actually shows our Milky Way and all the gas and all the intervening material that you had to figure out how to remove in order to get at the background, cosmic microwave background. How do you go about figuring out what is cosmic microwave background and what is foreground interference?
So this is a really great question. It's quite a difficult one. It's quite a difficult job to do. We spent a number of months and even years to really refine this analysis and separate the components. When you see this map, indeed, you see that in the foreground, sorry, we have the galaxy. So you see here in this projection, you see the galactic plane as the horizontal plane, and you see that the galactic emission, in fact, extends quite away from the plane, even at high latitudes. And what you see really at high latitudes here are the fluctuations in red and yellow here in this map. But you see that they are quite hidden, but what you see in the galaxy. So how do we separate this? There are different methods, but basically we use information we know about the spectrum of each of these components. So, for example, we know from other experiments that the cosmic background has a perfect black body spectrum. So we know its temperature. So we know more or less that if we observe at certain frequency, then we know that at a different frequency, the cosmic background will have this same shape and will have that intensity. And for the other components, we don't know as well as for the cosmic background their spectra, but we also have a pretty good idea of the spectra. It's the case of the galactic dust, for instance. So we know that it's kind of a gray body spectrum with a different temperature between, say, 10 Kelvin and 30 or more. We have an average high latitude temperature of the dust that's about 17K. So this helps to separate the different components. Of course, this we can do only because with Planck, we have multi-wavelength observations. We observe 9 different wavelengths of frequencies. If we did not observe in so many frequencies, we will not be able to separate the components, and we will not be able to show full sky CMB maps as was shown before. So it's very important to do this multi-frequency analysis.
So thanks to this very careful multi-frequency analysis, you're able to systematically figure out, okay, this set of has this amount of pollution from foreground objects. And as you clear that away, you end up revealing this amazing background that the variation in this is 1 part in 10,000, I believe. And that means that at the moment, or moments, as the case may be, that this light was emitted, the universe was the same temperature to that 1 part in 10,000 level. Is that correct?
So at that time, the universe was very homogeneous, and it still is actually on very large scales today, but it is very inhomogeneous at small scales, let's say. At that time, the universe was very homogeneous, even at small scales. So you had a very homogeneous background here, and these fluctuations, they are really very tiny. Yeah, so then they grow up, and they are the seeds of the large inhomogeneities we see in the universe of today.
So when the universe formed, we had this moment where everything was extraordinarily hot, so hot that there wasn't even matter, so dense that physics didn't work the way it does in our modern universe. In fact, all of the forces initially were combined into one. As things expanded apart, they expanded and cooled and expanded and cooled, and we began to get regular matter. The forces separated, not in that order. And it took time, though, to get to the point the cosmic microwave background formed. And that number has actually evolved since I was a student and you were a student. I remember learning it was 300,000 years after the Big Bang the cosmic microwave background was formed. Um, what do we think today is the rough age of the universe when the CMB was emitted?
So today we have refined this measurement and we estimate it to be 380,000 years after the Big Bang. So it's not so different from what we learned, 10 years ago. So um, now, of course, there are lots of things that happen between the Big Bang and the cosmic background. So we really don't know much from observations before the cosmic background, because this is really the first direct observation that we have. Because after this point, we are very lucky that more or less everything is transparent in the universe. But before that, everything is opaque. So we don't observe anything. But of course, we have theories, we have mathematical models that allow us to extrapolate into the past and to have some idea, or a pretty good idea already, of the history of the universe from the first instance to the microwave background. What we don't know at all, is what happens at the very beginning, because this is, as you said, uh, we're talking about energies, and we're even talking about the singularity, mathematically speaking, meaning that we cannot apply the physics that we know. So we cannot apply general relativity to the Big Bang time. We cannot apply quantum theory. So we start to understand physically what's happening already after, let's say, at least the Planck time. That is the very minimum time that we cannot go into after the Big Bang. But this is a very tiny fraction of a second, and then we try to figure out what's happening. So uh, little by little, things start to form. So first of all, matter and energy form. So separates. Let's say we have the appearance of the different forces we consider today the fundamental forces of the universe. And then we have the nucleosynthesis. So we have the basic particles, what we call the baryons today, the particles of normal matter, and the leptons, or basically the electrons that are created. And then we have nucleosynthesis, very limited nucleosynthesis. We form helium, and we form a little bit of lithium and beryllium. So that's the Big Bang nucleosynthesis part. So at that point,
And
you have the soup
and
of the elements.
and to make it clear, the reason that that happened is for a period of time, the entirety of our universe was so hot and so dense that it wasn't exactly like the core of a star. The physics was slightly different because the parameters were slightly different. But the entire universe was so hot and so dense that it allowed nuclear reactions to take place for a little bit of time. And that's kind of amazing to think about, considering how much work we have to go through here on the surface of the Earth to get nuclear reactions to take place.
That's right. So we have the conditions for thermonuclear reactions, so fusion of hydrogen nuclei, so protons, to fusion into helium nuclei. That is, that you have four protons that combine together and form a helium nucleus. So these are the conditions in the very early universe. We have kind of similar conditions at the heart of stars today. Indeed, we also have thermonuclear thermonuclear fusion of hydrogen into helium. That's what happens in most stars, in stars like the sun. Of course, the stars do a lot of other things, because they don't only transform hydrogen into helium, but the stars do other things that the Big Bang did not do. That is, that the stars also create more heavy elements like carbon and oxygen and other elements and metals and iron and so on, that of course are created only in stars, in fact, not before the stars existed, which also tells you something about the importance of stars in the history of the universe.
Now, one of the ways that we work to prove that our understanding of the Big Bang is true is people will do detailed calculations based on our understanding of how the universe was expanding that predict the ratios of how much hydrogen there should have been, how much helium there should have been, how little lithium, how little beryllium. And then we look around our universe to try and find examples of pristine clouds of materials, the youngest stars, to try and match up the ingredients that we see in these parts of the modern universe that reflect the original ingredients after the Big Bang. This is essentially the elusive hunt for the population 3 stars, is what we refer to them as. Um, what are some of the things that we look for when we're looking at the amount of helium that's out there, the amount of lithium that we see in stars?
So there are different things. Of course, yes, the study of what we used to call the population 3 stars is important because these are supposed to be stars in the first generations or the first generations of stars. So if we study their composition, we can verify that our theory about the Big Bang and the Big Bang nucleosynthesis are correct or not, because then we would see the composition, we would see the amount of hydrogen and helium and so on. Now, of course, it's not so easy to find these pristine stars because we are 14 billion years after the Big Bang. So there has been the time for many generations of stars, and not many generations of stars like our sun, because small stars like our sun live for a very long time. They are very slow considering, burning their hydrogen. They need a long time to burn. They're very long-lived stars. But of course, in the early universe, what happened is that there were mostly only hydrogen and helium, and the problem with that is that the collapse of the clouds to form the stars was really quite quick, and the friction was not so efficient as it is today, because it's the heavy elements that create mostly the friction. And if you have less friction, in fact, what happens, it's quite complicated, but what happens is you tend to form really big stars, and big stars are hotter, so they burn their hydrogen very quickly. So there has been already quite a lot of generations of these stars, and that have created all the heavy elements. So, well, we can thank them for that in a way, because otherwise planets would not exist. At least planets like the Earth, because planet like the Earth is not made out of hydrogen and helium, as you know. It's made of oxygen and silicon and carbon and many other things that we need also for life.
So we have currently cosmic microwave background is one of the leading pieces of evidence for the Big Bang. We look at the isotope ratios when we go out and measure how much of the different helium, lithium, and things like that are out in the universe, trying to narrow in. Um, as well as getting at the Big Bang with the cosmic microwave background, we can also start to see a reflection of how the universe would continue to change moving into the future. When we look at this map of the slightly hotter and slightly colder spots, there's different sizes to this, and all of this has meaning. Can you highlight some of the other science that helps us understand the evolution of our universe that comes out of looking at the cosmic microwave background? And I'll bring the map back up.
So we know also that the universe is in expansion, and we know that not only from the existence of the cosmic background, but from other things, like we can see the spectra of galaxies, we can see they are redshifted, so they're Doppler shifted, so we see that they go further away from us. So this is something that tells us that the universe is in fact expanding. Recently, we have also observed that the universe is in fact at the moment accelerating. So all this um, creates, let's say, a full story of the universe that we start to see, and from the cosmic background to today and to the very far future. So, of course, the regions in the cosmic background that are already over dense are going to become more and more dense, and the opposite for the voids. So what happens today? We have a structure of the universe that is quite clearly, say, divided into very large voids, and then structures, filamentary structures with superclusters of galaxies. Then, if you look into the supercluster, you see clusters of galaxies, and inside you see galaxies, and inside galaxies you see all kinds of things like stars and planets. Then the view we have of the future is that, according to our measurements, we can see that in fact the acceleration is probably going to continue. So that means a number of things, among which the fact that in the distant future it will be impossible to observe anything outside our local group of galaxies, because the acceleration of the universe makes that, okay, you know that we are limited by the horizon, that is simply the distance that has been that is defined by the speed of light. The speed of light is finite, so we always have a horizon that is when we see the Big Bang, or in fact the cosmic background. And with the acceleration of the universe, in fact, less and less galaxies outside our local group are going to be visible. So at some point, we're going to have real trouble making cosmology. But this is really going to be in quite a number of billion years, so not to worry for the moment. But after that, the universe goes on expanding and expanding, and at some point it becomes in a state where there is not so much going on anymore, because at some point all the stars will have exhausted their fuel, and so on. So the universe is going to be in a pretty cold state at some point.
It's a somewhat bleak future if you think about it. We currently live at, we don't like to think of saying that we live in a special place or a special time, but we do actually, given the fullness of history, we do live in a somewhat special time that allows us to see enough of our universe that we can start to piece together an understanding of how the universe has evolved since the Big Bang, since the cosmic microwave background was produced, and allows us to understand what our future will look like as the structures continue to expand, as we begin to run out of fuel to form new stars, as the existing stars begin to die out. And it's actually basically heat death of the universe is what we have to look forward to. So we started so hot and so dense that even the forces were combined, and we're looking for a future where everything is so diffuse and so cold that even normal matter as we experience it today probably won't exist in the furthest future.
That's right. So at some point, we think that all the normal matter will have collapsed into black holes, because the black holes are kind of the ultimate state of for stars. They cannot collapse more than that. The black hole is the ultimate collapsed star. It's a singularity itself. So, but really, we don't know really much about black hole, in the sense that we don't really know if the singularity exists or not. We can imagine intermediate states of matter between, say, the neutron star and the black hole that could exist. But in any case, the gravity makes that at some point, by chance encounters over very, very long periods of times, we have every matter, or most of the matter, into black holes, and the rest of it is essentially free electrons flying in the universe. And the universe is so expanded, and that they don't even encounter each other. So this is a pretty bleak future, as you say. Now, it's not completely clear that this is going to be the case, there, in the sense that this is the preferred view of that the data give us today. But in fact, some small change in the preferred parameters, in some of the preferred parameters that we fit to our data, could change quite a lot. It's not completely clear that we don't at some point experience change in the direction of the expansion of the universe. And in fact, the universe starts crunching, and until there is a big crunch and then a new Big Bang, or that there are alternative theories as well that considered that there was no real Big Bang, but that there are other dimensions out there, and that through these dimensions you could have different, let's say, membranes oscillating, and then at the moment of these two membranes touch each other, we have another kind of Big Bang, and this. So there are many theories out there. The standard one says that indeed the universe will end up in a state of heat death, but this is not really confirmed.
And that's part of the reason that we need to keep building missions like Planck, and we need to keep working to move our understanding forward with more and more data. There are the way I heard it phrased once is if you take 20 theorists and lock them in a room, they'll come back out with 30 different theories.
At
Um,
least.
so it's still unclear exactly what our future is, and we're still working on the details of how we got here. But we do have a big picture understanding that is completely consistent from theory to observation, that we live in a universe that was formed through something that we have awkwardly labeled the Big Bang, that was an expanding universe that is evolving structures over time. Now, we have a question that's come in from the audience, and I will remind everyone out there that if you have a question, just click on that Q&A app on the browser window where you're watching this, if you're watching it live, and we will work to get to your questions as we can. Adam Synergy asks, how many scientists are there in the Planck team, and is it difficult to write a paper with so many co-authors?
So this is a very good question. We have more or less 400 scientists in the Planck collaboration, so this is quite big. There are bigger ones, of course, but this is already it creates some issues indeed when we write papers, and we have full process of internal refereeing for the papers and so on. Not everybody signs all the papers, but in any case, it's quite challenging in terms of management of the team. That's true.
So we've had you here for 30 minutes now, and I should let you go and get back to your evening and start to cover the lesson plan that we have for our teachers. But before I let you go, do you have anything that you'd like to leave our teachers with to think about moving into the future?
I think one thing I would like to say is that although it's true that we have a consistent picture of our universe, there are many, many areas where we really don't know anything about. We know, for example, that most of the constituents of the universe are dark energy and dark matter, but we know very little about either of them. We also have lots of periods in the history of the cosmos that we don't know much. We don't know much about the dark ages. We don't know much about the period where the first stars form and starts reionizing the universe. And this is a field that is going to be very important now in the coming decade. That people are now starting to study how they are going to be able to observe these times, roughly 200 million years after the Big Bang. And this is to say there are really lots and lots of things to do in cosmology. It's not just the cosmic background and the expansion of the universe. There are plenty of things to do. There are plenty of things to discover. Also, we have this story of the gravitational waves, the BMOs of the cosmic background polarization that is not at all solved. And so we have really many things to do. So I think it's quite important to study cosmology and to make sure that also children, students are aware that this is a very interesting topic, and that I'm sure some of them will want to be cosmologists and will be able to do so.
That sounds awesome. Thank you so much for joining us, Xavier. And if people want to learn more about what you do online, where should they look?
Well, they can have a look at the ESA website or at also the archives, the Planck archive in the ESA website. So if you look at the ESA website, you should have the links for all the other things.
Thank you so much for joining us, and have an excellent rest of your day, and keep doing the awesome science.
Thank you. Bye bye.
Bye-bye. So, for those of you who are staying, we're going to be spending the rest of this hangout talking about a lesson plan that is being put together to go in the Open Discovery Science portal, where you can find all of the inspiring science education lesson plans. Now, in teaching kids about the Big Bang, one of the easiest ways to teach it is to go through essentially the history of how we came up with the different lines of evidence and to let them use inquiry to understand the different points that made people think, I wonder if the way I currently understand the universe is right or is wrong. One of the first lines of evidence that we had about the universe, well, having some sort of an origin, maybe, was back in the 1800s. A German, depending on where you look, he's listed as a philosopher, a physician, an astronomer, um, Heinrich Olber. He was trained as a physician, got sidetracked by maths and astronomy, ended up doing a lot of excellent astronomy work, including discovering the asteroid Pallas. Uh, he one day got to thinking about our sky, got to thinking about the fact that when you look up at the night sky, and I'm going to pull up an image to share, when you look up at the night sky, what you find is the night sky is dark. And that doesn't seem like it should be an odd thing to think about, but it was actually quite surprising as he started to think on what that meant. So this is a image of the 2009 Hubble Ultra Deep Field. This is one of the deepest images, which means one of the images that looks for the faintest objects that can be seen that has ever been taken. And where you see darkness in this image, there really just isn't anything to be seen. This image is looking at an area of the sky far smaller than your pinky fingernail with your hand held out at arm's length. And in this image, there are hundreds and hundreds of galaxies, but there's still darkness. And what Olber started to realize as he thought about this is if we live in a universe like they thought we lived in back then, that is completely infinite in size, with everything being basically the same in all directions, that the universe can't also be infinite in age if there's going to be darkness. Now, the demo that you can do to help your kids understand this is pretty straightforward. Rather than do the actual demo for you, because it's quite messy and hard to capture on camera, I'm going to show you a basic simulation of it that I put together in Illustrator. You can also do this in PowerPoint in a similar way to what I'm showing now. So what you'd want to do is go outside, someplace that you can draw on the sidewalk or the pavement with a piece of chalk. Take a bag of rice with you and a rock that you can tie a spool of thread around and have a long spool of thread. And when you go outside and you scatter the rice, you'll end up with a large, sorry, I'm trying to share my screen and talk at once. You'll end up with essentially a large speckled region that you're looking at. So here's the large speckled region. Just pretend this is asphalt with lots of rice scattered all over it. Now, if you take and attach a piece of thread to your weight, you can now take that piece of thread and rotate it around. And as you rotate it around, and of course on air, it doesn't want to let me rotate it. Technology knows somehow. Okay, so pretend that I could rotate that around. Let me see if I can do this in a different way. As you rotate your thread around, what your students will notice is pretty much all the time, your piece of thread somewhere cuts across one of the grains of rice. So again, all the little white dots in this are your grains of rice. So as you move the thread around, say this piece of thread is simulating you looking out across the universe. And every time the piece of thread intersects with a grain of rice, that means that where you're looking, you're seeing something bright in the sky. Now, in this example, looking at the entire universe, you pretty much can't move the thread around without it crossing a grain of rice. Now, if the entire sky was such that everywhere we looked, our eyes intersected a bright point of light, the entire sky would glow with the light of a billion suns, but that's not what we see. So here you can say, well, let's look at smaller parts of the universe. So take your piece of chalk and draw a set of circles. Try and make them evenly spaced. They don't have to be perfect circles. This is just a model to get your kids thinking. And say that the innermost circle is the nearest 3 billion light years of the universe. The next one is taking you out to 6 billion. The next one's taking you out to 9 billion. And we're still assuming that everywhere you look, stuff is evenly distributed throughout the entire universe. Now, if you look only in this inner region, as you move your thread around, you start to see more and more moments, like right now, where the thread doesn't actually intersect with any of those grains of rice. So if the universe is small, it's easy to come up with moments where your thread isn't intersecting any of the grains of rice. It gets harder, though, the larger and larger an area that you look at. So get your kids thinking about this. What does this mean? Now, there's two different ways that you can look at this. You can either tell them, well, what if our universe was only 3 billion years old? Well, that means that light could only reach us from as far away as this first line, this first inner circle that you've drawn. Anything beyond that, it could be out there, but its light hasn't had time to travel from it all the way to us. So if we don't see that much stuff, it might be because, well, the universe isn't that old and it hasn't had time to reach us. But what if the universe was infinite in time, but only 3 billion light years across? Well, then you'd still only see light coming from those things in the inner 3 billion years. Ask your kids, is there any way to tell the difference between a universe that's only 3 billion light years across or 3 billion years old? Get them thinking about this and then imagining what it would mean that we do see darkness, that we do have points where that string that is our gaze across the sky, oh, it's not rotating, it's moving. Get them to think about what it means that we can see darkness and to talk about how it means that our universe must be finite either in age or in size or both. We actually can't tell. And you can explore all of this just by scattering rice on the ground and using a piece of thread to represent looking out through the universe. Now, it's kind of amazing to think that it was in the 1820s that Olbert came up with this idea and got people thinking about the universe. Now, the idea that our universe had a beginning was completely consistent with a lot of the philosophical and religious understandings of the time. But it was still a little bit disturbing to scientists who kind of wanted, because it was easier to think about, everything to be infinite in all ways, infinite in time, infinite in size. And the fact that it wasn't, that left people kind of going, I wonder what that means. Now, the next thing that came up historically was the realization that when you look out across the universe, you can use Doppler shifts. You can use the changing in what color light appears to be to try and figure out how fast something is going. So one of the prerequisite pieces of knowledge your students will need is the Doppler shift. Back in the 1910s, astronomers all over the world started to use new telescopes with devices called spectroscopes on them to start to measure what color do the hydrogen bomber lines appear to be. These lines created as the electrons in the hydrogen atom go from the third level to the second level, or from the second to the third, depending on what you're looking at. By knowing in a laboratory exactly what color that transition is supposed to happen at, and then going out to the telescope and measuring what color it appeared to happen at, it's possible to calculate the velocity that galaxies are moving at. And up until that point in time, it was totally expected that when we looked out at the galaxies, people would realize that some of the galaxies are moving towards us, some are moving away, and it's completely random, with a distribution that was either Gaussian or flat, or they weren't entirely sure what the distribution should be, but they expected it to be random. But once they had these new telescopes and these new spectrographs, they started to realize that the actual universe doesn't actually fit that idea of random. And it was actually work done in the American Southwest at Lowell Observatory, where they realized for the first time that the majority of the galaxies that we could see were actually moving away from us. So that was the first moment of, I wonder what on earth is going on. And this was followed by work in the state of California, out at Mount Wilson Observatory, that Hubble did, that allowed us to start to measure the distances to these galaxies. He used pulsating variable stars and followed on the work done by Henrietta Leavitt. And he was able to measure the distance using these variable stars to a variety of different galaxies. And what he realized was the galaxies that are further away seem to be moving faster than the galaxies that are nearby. What he knew this meant was the universe is expanding. Now, when you explain this to a kid is going to be like, why, if the universe is expanding, is something further away going to be appearing to move faster? If it's all expanding at the same rate, shouldn't everything be moving at the same rate? It's an easy misconception to come to. So in this particular lab, we have an inquiry activity designed to get your kids to model the expansion of the universe and to actually start to put the pieces together to understand, oh, things that are further away do appear to be moving faster because there's more stuff expanding between here and there. And it's also designed to help them understand that our universe doesn't actually have a center, because the other misconception a lot of people come to is, as our universe is expanding, the reason we see everything moving away from us must be because we're at the center. And no, that's actually not the case either. No matter where you go, you have the same perspective of everything moving away from you. So I'm going to switch over to show you. This is an activity that was put together using Google Sketch. So it's entirely free software that all of your students have access to. You can also do this in Adobe Illustrator. And if you really don't like yourself, you can do this using PowerPoint or other software like that, but it gets really challenging. So I'd encourage you to go ahead and use something like Google Sketch, and I will be providing a link to the illustration I put together so that you can copy it to use with your students if that's what you'd like to do. So let me go ahead and share the activity. Now, as I said, I've already done a lot of this activity for you. So I moved things out of the way so I can do it step by step. So the first thing that you start out having your kids do is draw a series of boxes, and each box represents the universe at a different point in time, where the smallest box is furthest in the past. And as the boxes get bigger, you're moving more and more into the future. You're watching the universe expand. Now, it starts off with different I use little explodey figures to mean galaxies, and these aren't actual colors the galaxies come in. You're not going to find a bright yellow galaxy. You're not going to find a purple galaxy. But these colors do make it easy to keep track of which galaxy is which in this simple model that we're putting together. So what you can have your kids do is grab this grid, copy it, and then just expand it to fit in this next box, and take and drag onto the same place the galaxies so that you can see where they've moved to. Now, rather than force you to watch me doing all of this, I have actually already done it ahead of time so that I can just bring it over and show you what it looks like. So looking at this, imagining that we're in the purple galaxy in the center. So that's us right there in the center. What you can see is the galaxies that are nearest haven't moved that much. So this one is 1 box away, this one's also 1 box away, and they both moved the same amount. This one is across the diagonal 1 box away, and diagonals are a little bit longer than sides. You can see that this moved even further. These 2 galaxies are 2 diagonals away, and you can see they've moved even more. Now, you can keep doing this for bigger and bigger systems. So I can drag in this box to show you what it looks like at the next stage. And you can see how that further galaxy appears to be moving the fastest across the sky. The intermediate ones seem to be moving slower, and the nearest ones seem to be moving slowest of all. And this is because the amount of stuff to expand that's between you and that more distant galaxy. Well, if there's more stuff to expand, it's going to, well, expand more. And you can see that directly with this. Now, since I did this centered in on us, the purple galaxy in the center, it's kind of hard to see that other galaxies might have a perspective that the universe is also expanding. So this is where these circles come in. So these circles allow me, if I line it up correctly, to see how, and I'm going to delete the intermediate step if I can do this correctly. There. So now we have 2 steps. You can see that in the first step, this inner circle passes through the green galaxy and the orange galaxy. In the next step, it passes again through the green galaxy and the orange galaxy, because those 2 galaxies are the same distance away. Now, what if instead I was on the green galaxy? Would I still see things expanding away? So let me move this over here and now center my circle on that green galaxy. So now I can see there's the purple galaxy lined up there. Now for the next stage, I'm going to line this up on the new location for the green galaxy. And I can see that I still see the purple galaxy moving away. You're going to have to talk your kids through this. And you can actually have them, instead of using these circles, for some of them, it might just be easier for them to understand if you just have them move the grids around. So you can actually grab the set of grids and have them move the grids instead. All of this together allows them to entirely explore how we see our universe expanding. You can have them make plots of how much things at different distances appear to move away, and get at the expansion rate for a constantly expanding universe. You can play with it to have it expand at nonlinear fashions if you want to make the project more complicated. And all of this is done just using a simple line drawing application that you have in Google that's available for free for everyone out there. So the final part of the puzzle is something that you can hit on with your students, but it's not something that we can really do an inquiry activity on. And that is looking at how do we understand that our model of the Big Bang is accurate based on what should have been formed during the Big Bang. And the easiest way that I know to get at this is to say, okay, let's imagine that we have a system where we have all the building blocks in the early universe to create 75 white Legos and 25 red Legos and one or two blue Legos, making these Legos pretend to be the hydrogen, the helium, the lithium that make up our universe. And then give the kids a variety of different objects that are made up of small numbers of Legos and have them take them apart and count up the ratios of the different Legos and figure out, is it possible that these different models support that early understanding that we have? You can make this even more complicated by doing things like saying, well, what if blue and red Legos combined to make purple Legos? Sort of like in our own universe, we see those original building blocks, that original hydrogen and helium, getting reprocessed to form heavier elements like silicon and carbon. This is a way to get your kids to think about, how do you eliminate theories and how do you simply test them and say that what we see is consistent with what was predicted, but because the universe is evolving, we can never actually get all the way back to what was originally predicted. A lot of this lesson is focused on getting the kids to think creatively about how what they see can limit a theory or rule it out altogether. Olber's paradox, that initial scattering rice on the ground exercise you had your kids do, that helped them understand that we can't live in an infinite universe with an even distribution of galaxies as far as infinity can reach. This expansion activity is designed to get the kids thinking about how there is no center and how you can understand expansion leading to things that are further away moving faster. This is one of those lessons that may not be as satisfying as a teacher because there's going to be a whole lot of words to grade and not a lot of numbers to check. But it's the type of thing that gets your kids really thinking through a lot of problem solving. Now, all of these lessons, they do go up in the Open Discovery Space portal. Just Google Open Discovery Science, Inspiring Science Education. And all of this goes into a community that's called the Big Bang Community. So go ahead, join us. It's all part of the Discover the Cosmos community, which is our main community. So if you join the Discover the Cosmos community, you'll be able to dig down and see all the different lesson plans that we've created as part of this series. We also be linking to this in the show notes on YouTube once everything has been proofread and put up online. I'm not seeing any questions directly related to the Big Bang in the Hangout questions right now, and I have kept you for about an hour. So if you have any questions, don't be afraid to reach out to us. And if you have any thoughts on how to modify these labs to make them work for more advanced learners, to work better in places where maybe you don't want to be scattering rice outside because there's too many birds that are going to swoop down and try and eat it. If you have ideas for how to change these labs up to work better for your community of students, everything that we do, you are welcome to take and copy and clone and evolve it to suit your needs. The only thing that we'd ask is take a moment to share back with us what it is that you've created. Together, we can make these learning tools fit every type of educational community that's out there. But it takes you taking the time to share what you create back with us to make this learning community possible. So I hope I'll see all of you online, and I'll see the new lesson plans that you're able to create out of these starting points that we've provided. So thank you very much for joining us. This was originally scheduled to be the last Hangout of this particular school year. However, due to illness, first on my part and then on the part of the scientist who was joining us, our lesson on blackbody radiation has been multiply delayed, which we're very sorry for. We are still in the process of trying to work with the scientists to reschedule when that will be recorded. So stay tuned. Watch for the announcement to come out. Subscribe to us on YouTube. And as soon as it goes live, you'll get it in your feed. So we do have one more surprise episode that will be coming out as soon as both me and our scientist can simultaneously be healthy and be free. So stay tuned to learn about blackbody radiation, and we will be back in the next school year. New topics, new ideas, new guests. So have an awesome summer if you don't come back for the blackbody lecture, and we'll see you in the fall. Thank you.